Thank you, Radical, for the introduction, and thank you, everyone, for coming to my talk. So today, it's my great pleasure to introduce our research work on providing a security alternative solution for 5G data plan. And this is a joint work with my colleagues at UCLA and my advisor, Dr. Songwu. So our solution is simply based on an observation right here that 5G data plane is not secure. Okay, so to better understand it, I will first provide you with some context in terms of 5G and in terms of 5G data plane security measures. So as we know, 5G is a popular large-scale system to provide anytime, anywhere services. It is probably the only large-scale system right now that can do such. And to offer such nice features, it adopts an architecture as shown here. On one hand, we have the 5G devices, and we have the base stations that cover the geographical areas and provide the wireless access. And we also have the network core that provides the backend services and also bridge the base station and also the internet, such as the cloud and edge servers. So given such architecture, basically the function includes the control and data planes. Control plane is responsible for session and state control, and it has some major functionalities like security, mobility control, radio access control, etc. And these messages are usually happening at the very beginning of a session or when some certain events happen. So which means that its security it's more infrequent and its security is more well studied. On the other hand, the data plane is in charge of the per packet data delivery. It includes both data and data plane signaling. Unlike internet, whenever you want to send some data, you have to go through those complicated signaling procedure before you can actually do so. So let's take a look at how 5G data plane protects its data and signaling. So first, we notice that the data plane packet delivery is not secure. So what is the current measure being taken in the 5G data plane? Let's say we want to deliver a data from the device to the base station. And the first practice it takes is try to encrypt it. So both senders and receiver, they will share a symmetric key, and only the receiver that has this key can correctly decrypt the data. And the second measure is to take the integrity protection. So how it works is that they will calculate a cryptographic hash based on the encrypted data and attach that integrity code to the data. And the receiver who has the key can use this integrity code to verify whether the data has been manipulated or not. It looks great, right? Every data is protected well in terms of authenticity and confidentiality. But the problem here is that the integrity protection in 5G is actually optional. Well, technically, starting from release 16, 3GPP says, well, we should have this kind of mandatory integrity protection. It's being standardized. But the problem is that such procedure is still negotiation-based. And those applications that has very high throughput can still use no integrity protection, not to mention for the legacy devices as well. You might also ask, well, we already have the encryption, right? So it looks like that if the data packet is encrypted, why not should we worry about whether the data packet can be manipulated or not? But the reality is that due to the overhead issue as well, the data encryption is using very simple algorithm, and the researchers have shown that as long as you can access the data, you can actually change some bits to change the content there as you wish. So even with the encryption, this is not secure. On the other hand, it's not working. All right. On the other hand, we have the data plane signaling messages, which is used to facilitate data transfer. So they are actually kind of like important messages, just kind of like a gray area between the control and data plane. They are also used to manage the data plane delivery. It has some major functionalities, including some commands that base station asks the device to do something, or some status sync up, so they exchange messages to update their power status, etc. So even worse than the data packets, these signaling messages, they are not protected at all. They are sent in clear text. So there are several attacks that can be used to forge these kind of signaling messages and cause serious damages, such as drain the power, drain the resource in the radio, and also reset the entire connection. So we have lots of discussion on the paper. If you're interested, take a look. And these are absolutely not just stupid mistakes, right? As we mentioned, the overhead is like one major concern for such kind of design choice in current 5G. So according to some study and our own measurements as well, integrity protecting every single data packet could incur even 70% of extra overhead. This is not a small number. And also some other reasons, including, for example, some signaling messages that are in the lower layer, they don't have any security context because that context is in the higher layer. So this motivates us to think about another question. Can we design an alternative solution, a system that can reactively detect and mitigate such threats? So to this end, we designed CellDAM. So here's an overview. It includes 3 major steps. First, it will try to capture the data. Second, it will inspect the data and to find out if there's any ongoing attack. And third, if there is, it will launch a mitigation procedure, try to fix it. Of course, we have to keep some design goals in mind, right? So the first is that we talk about the overhead. So this solution must have 1 to 2 orders of magnitude lower overhead compared to the current solution. And also, it should work without additional privilege. Like, we cannot assume that any user has access to the firmware or has rooted their phones. So we talk about inspecting first. Let's assume that we have all the data ready, and how can we use this data to find out whether there's any ongoing attacks. Our design takes a very clear guideline, that is, we try to verify what's correct. So we are not targeting a specific threat model or something. We just say that, hey, this is the correct operations. We model it, and then we verify that if the current operation in the runtime follows this operation as we expected. And if it is not, we say there can be potential issues as potential attacks. So for this one, we have made a very important observation that instead of monitoring every single data packet, we can simply verify the signaling messages. So remember that data plane has its signaling messages to facilitate its data transfer. And by verifying these signaling messages, we can actually detect both the attacks against data packets and data plane signalings. And even better, it's 1 to 2 orders of magnitude lower compared to the data. So why is that the case? For data plane signaling attacks, it's quite intuitive, right? If the attacker tries to send a malicious data plane signaling, it must arrive in a very wrong context to trigger some serious damages. But for the data, it's less intuitive, but let's make a simplified example here. Let's say the attacker tries to forge a data to the base station. And this forged data will trigger an unexpected acknowledgement to the device. So actually, by monitoring the signaling, the device can say, well, I didn't send data before. Why am I receiving this acknowledgement? So this is an effective approach to detect such kind of attacks. So now we have our goal, which is to verify the signaling messages. Now, how to do it? So there are several design choices. The first option here is for each protocol to verify its own signaling. As we can see here, 5G incorporates multiple protocol stack for different functionalities. So one obvious choice is that every single protocol takes care of own signaling messages. But unfortunately, this will not work. The problem is that some certain attacks must be detected by a cross-layer approach. Let's say we have received a malicious RLC, NACK, which is a message for retransmission. But the problem here is that it's quite natural and common for RLC protocol to receive a retransmission request, right? Why not? But here the issue is that if you observe the MAC protocol, probably the MAC, which is a layer protocol, will tell you that, well, I haven't finished all the procedure and sent out this packet. Why the other side asks you for a retransmission? So therefore, by combining these two protocols, there will be some actual interesting findings that this message cannot exist in this current state. So our insight here is that we must design a cross-layer verification for such kind of signaling messages. So for cross-layer signaling verification, there are also some choices. One option is to use the state-independent checking. Like we just design a list of checks. And whenever a data comes, we just check it based on the protocol or headers of different protocols. But the problem here is still, it will fail to detect certain attacks. Let's say we receive, again, a non-acknowledgement here from the RLC protocol. If the MAC layer says, well, I have finished all the procedures, then this message will be legitimate. But on the other hand, if the lower layer hasn't finished its procedure and sent it out, then it will be impossible to receive such a retransmission request. Therefore, we must design a solution that is state-dependent. So consider that our solution, CellDAM, takes a state-dependent cross-layer checking approach. And it applies checks based on the current state. So you receive a message, you check it based on the state. We have a list of checks here. And then afterwards, we maintain such state based on the received messages. We will change the state based on the incoming messages. So there are some construction here. I will just omit the details here, but if you're interested, please refer to our paper. So based on the state machine and the checks, based on the state machine we constructed, we have also devised several checks here. There are several categories of checks. For example, checking whether the incoming message type is being expected in the current state, like checking whether the state is consistent, or checking whether the timing of this incoming message is expected or not. So one typical example right here is checking whether the message type is allowed. Let's still use the previous example. So we know that if the MAC layer is in this specific state, and if the RRC receives such message, it is not possible, and it's kind of like being well represented, cached by such kind of our checks. For example, in this MAC pending state, this RRC NSDI is not being expected in the current state. All right, looking great. We have now devised a solution to verify the signaling to detect the issue. But the problem is that how can we capture the signal? On the first side, it's pretty straightforward, right? If we just implement something in our device, especially with the firmware access, we just or with a rooted phone, we just directly install some software and access all these messages and see if these signaling messages and apply our method. But the problem here is that there are some specific scenarios where we don't have the firmware access. So our solution here is that we use a separate node to capture the signals from the device. So in our system, we have a separate device called SecHub or Security Hub, which will capture the wireless signals for this protected device and then use our algorithms that we described before. So how it works? The challenge here is that you have no idea, like over the air, which signals are from or to the protected device. You have to recognize which device is for which. And the problem here is that different device will be assigned with a different physical layer ID. That is the identifier for different device to recognize whether this message is for me or not. So the problem here is try to infer the physical layer identifier. How to do that? We use a watermark technology where the security hub or SecHub here will communicate with the application, which does not need firmware access, on the phone device. And it will define a pattern. So this is a simplified version, like 40, 80, 80 bytes. And then it will initiate some data packets to the base station. And by checking which physical layer ID actually has such kind of pattern, it will recognize which device are the device that I intend to protect. And of course, we have some other technologies like how to keep the physical layer ID unchanged or how to preserve the privacy, etc. So please refer to our paper. Now, what if there's any threats being detected? The next step for here is try to devise a mitigation approach. So our key observation here is that usually an attacker tries to send some malicious data or try to attack you is always being camped on a single cell, that is the cell you are currently using. So if we can elude that, right, by switching to another cell, that can probably avoid the attacker. And our idea here for CellDAM is to leverage the existing handover procedure. Handover is the procedure in 5G which transfer the states of a device from one cell to another cell. And it has some nice features. For example, it has very short disruption, because after the handover, all your states will be transferred to the new cell as well, so you don't have to reestablish the connection. On the other hand, the handover messages are encrypted, so the attacker cannot track you to the new cell. And if you have the firmware access, then it's pretty easy, because you simply have to send some measurement report to trigger a handover. But if it's not, we also use our security hub to send some noises to affect the measurement results so that it will manually trigger a handover later as well. So it doesn't require any root privilege. So we implement our solution, CellDAM, with the software-defined radio. We have the implementation using the USRP boards and SRS RAN. So the evaluation result is shown as follows. We first try to see if it can indeed detect those threats. So we can see from the table right here, it can detect attacks including both that targeting the data packets and also data plane signaling messages. As we can see here, I marked 3 attacks as new attacks here. It's not actually that we manually find out these new attacks. It's actually being inspired by our approach, where we have like a state machine, and we also have a list of checks. We just enumerate the checks on a state machine to see what are the possible attacks available, and figure out 3 new categories of attacks here. So actually, this will, if we have like a modeling and we use this kind of checks, we can always try to find out these new undiscovered attacks before. And our solution can also trigger handover with 100% success rate. These benefits all comes with little cost. So our solution is low overhead in terms of processing, where it generates 0.9% overhead compared to the per packet processing. And in terms of mitigation, because the handover procedure only has very short disruption, it will incur around 72.3 milliseconds. That's pretty much for CellDAM, and here are some takeaways for this talk. We first show that detection and mitigation is a very important alternative reactive approach to security, especially here for a 5G data plan. And the main philosophy here is try to ensuring what's right. It's actually on two different levels. First is that we try to verify what is correct to find out those potential attacks. On the second level, it means that we try to verify what's the correct component to verify. Like in this case, it's signaling, which can greatly reduce the overhead for our solution. And finally, we also see that from the system perspective, we can build a separate node to handle all the signaling messages and handle all the security approaches without the root access. So thank you very much. I'll be happy to take any questions.